So these three options. If anyone who's implemented a new control system, say you're going with an Allen Bradley controller and you want redundancy, the first thing you're going to look at is, well, what's their solution for redundancy? And most PLC manufacturers' solution for redundancy is CPU only, which is what's one of the things that's attractive about it. It's a canned solution. It's easy to implement. You pretty much plug and play the components, select the box and the software that you want redundancy, and there you have it. There are some downsides that need to be considered, though. These systems are not really designed for single system controllers. They're more designed for a master control unit running, say, 5 bottling lines in a bottling plant. So they're not designed for a single system, a single exciter, a single governor, a single unit controller. There is some decreased PLC performance in the overhead. They're not designed for speed optimization. And you still have many single points of failure. One I/O module is still going to take your unit out. So while you're replacing your CPU, it's just one component. So the next step would be, let's have redundant I/O across the board. And usually you'll see this in 2 fully redundant controllers running the exact same set of hardware, running parallel programs that are operating in sync. Now these often do require custom engineering. But because of that, they can be optimized and configured for your arrangement. So your performance impact is minimal. It's going to be seamless to your normal operation. And in your controller, you'll now have no single point of failure. Any controller component can fail and the unit will keep running. You'll lose some robustness because you're under your backup, but you can now take an outage at your convenience. This still leaves single points of failure. These 2 controllers come to consensus and say, okay, we're going to open this actuator. Well, what happens if the relay that opens the actuator fails? Or what happens if the valve that opens the actuator fails? And this is where things really start getting into a gray area. You're kind of going down the rabbit hole of where do we stop? And you need to look at the device, look at the likelihood of it failing, look at the cost of it failing. You'll often see redundant hydraulic controls. Less often we'll see redundant relays because of fail-safe logic and how they operate. It can get really complicated and give intermediate states of failure. So this is where, I'm not going to go into much more detail, but can you really eliminate every single point of failure? What are you trying to, are you trying to solve just a mantra of no single point of failure, or are you actually making serious improvements? And then also, what are your common modes of failure where if you're talking about field devices, you're talking about devices that say dirty oil going to 2 valves, maybe having 2 valves isn't giving you that much bang for your buck anymore. Okay, so when would you want to use these types of systems? They're all valid configurations. So I'm going to choose a few utilities we've worked with and show you their situations that drove to the decisions they made. Brookfield Renewable Power has many hydro installations in New York and Maine. Many of them are under 10 megawatts, small units. So they chose fully simplex equipment. 1 power supply, 1 controller, 1 output. They have, at under 10 megawatts, their lost generation costs are less. If their unit goes down, they're relying on that energy, but they have 40 other units in a 20-mile radius that are also generating. So your cost for a single loss is less. And there's less impact of that loss. These units are regulated less, so there's lower fines. They're not required to pass the same quantities of water. So failure is tolerable. The next level, we're doing a project with the Army Corps of Engineers and in the Pacific Northwest. Most of their units are in the 50 to 100 megawatt range. The lost generation costs are starting to go up at this point, where a unit going down at 100 megawatts in the peak of summer is a significant impact. But in their favor, these plants have redundant units. So maybe unit 7 goes down, unit 8 wasn't running at the time, they can bring that up. So there's a level of backup there. So these aren't critical failures, they're costly failures, but they will not result in any significant fines, and there are backup options. That's why they choose redundant sensors and power supplies. And it's also the best bang for your buck. It's the easiest to implement, and it gives you the biggest boost in availability for the least cost. Now the final situation, Pacific Gas and Electric in California has a lot of large units, well, a few large units, over 400 megawatts. They also have a lot of water conveyance responsibilities. These are the guys who are California, the valley, irrigation, recreation. If they can prevent a single forced outage that results in a loss of flow, that might cost them $100,000, $200,000. If they can prevent a single event by going with a redundant system, it pays for itself. These are the situations where redundancy really comes into play. You'll hear it, I mean, you wouldn't think twice about redundancy on the plane you flew in on because it's a loss of life situation. Anywhere where a failure is not acceptable, that's where you're going to see redundancy. Now, on top of the decision making of what level of redundancy, there are other steps you can take to minimize your mean time between failures. One thing you saw as a trend is as we increase equipment, you'll have more equipment failing. So minimize the number of components across the board during your design. Use high quality industrial grade equipment. Use protection, clean oil, clean power, filter your oil. And then a well-maintained, well-executed preventative maintenance plan will minimize the failures that can take your system out. So when equipment does fail, how can you minimize the amount of time it takes to repair it? One of the biggest advantages of modern control equipment is its enunciation power, where if you had a mechanical governor and you had a cable stretch and now it's out of calibration, you're not going to know about it. A modern governor will enunciate on that immediately, send an alarm not only to the local operator, but into your SCR and into your asset management system, whatever you're running. So with clear enunciation, you can identify where the exact cause of the problem is quickly, if that's set up properly. And then obviously training with the staff, the troubleshooting and replacing components practices. A lot of new equipment is being placed that the existing staff is not very familiar with. And thank you. And getting them trained. Available spare parts, not just stocked, but functional. How many of you guys have a spare parts shelf that's full of dust and the equipment was sent 20 years ago, and who knows if it works when you're going to need it? And then the components that are easy to replace. Finally, the steps to minimize mean time between forced outages, and this is really coming from your redundancy. You have various levels of redundancy that you may not even know about with redundant units, where if unit 1 goes down, you can put unit 2 online, if your generation planning allows for it, all the way through control algorithms, where maybe you can swap from an automatic control manually into a manual control and keep that unit online without replacing any additional. So between the various levels of configuration and some of these steps, modern controls can greatly enhance unit availability if that's the design point in the beginning and it's a logical design point, not just with a we want this unit available 100% of the time. Thank you.